All right, the third presentation is titled Bond Slip Damage of Concrete Structures Due to Corrosion of Reinforcement. It's given by Dr. ChangHoon Lee. He's an associate professor of civil and environmental engineering at Western New England University. He received his PhD at Cornell University and MS and BS degrees at Korea University. His research interests are chemical, mechanical property, transition of cement-based materials, characterization of multi-scale properties of cement-based materials, probabilistic assessment of material and structural performances, and temperature and moisture effects on sustainability of cement-based materials. Please welcome Dr. Lee.
Thank you very much for giving me the opportunity to give this talk. And also I appreciate my colleague, Dr. Shin, sitting over at the backside, working really hard together about this project and other project as well. And also I really appreciate to TIDC and the other industry companies who supported the materials, as well as fibers and chemical mixtures and everything. So I really appreciate their support to this project. So today, let me just start this way about my presentation. I've been enjoying all the presentation in the morning, particularly about the composite structures. So basically, I heard a lot about the corrosion issues. The corrosion is kind of monster that hurts the infrastructures. So my presentation is going to be really face off what the corrosion is. So I believe that you can just see some of the ugliness of the corrosion. And I'd like to just show you what's happening. I mean, what we have seen from the many experiments related to the corrosion. So let me first show you. I believe that this video is published by the media. Oh, thank you. So that is a Prudential Tunnel located in Boston. So this happened in the February this year. I believe that the Dr. Jiang Yu knows more about this one. So one of the reasons that they are still under investigation, but what they are thinking now is freezing and thawing, coupling with the corrosion reinforcement. The corrosion of the reinforcement triggered these kind of issues. So it's quite scary, isn't it? Because the corrosion is going to happen coupling with other durability issues. So that could cause this kind of sudden issues. So let me just first talk about the corrosion 101. Anyways, corrosion happens everywhere. So as far as oxygen and water exist, the steel is going to be corroded. Then chloride comes into play, then that corrosion process is going to be accelerated. That's simple. So that's simple. So as a result, steel is going to lose its mass. So which means that the cross-sectional area of the rebar is going to keep reducing because of the corrosion. On the other hand, whatever byproduct, we call it as a rust. So can you believe that that many different types of rust exist? But anyways, if those rusts are formed, then the volume of those rusts are 2 to 6 times greater than its original iron, which means that large volume of the rust is going to try to push out the concrete, and then eventually tensile stress is going to be formed, then cracking is going to happen. So as a result, you can just see that a lot of the cover is going to be fall off. However, we never know that what's happening inside of the concrete because of the corrosion. So let me just show you further. So basically, I just wonder that, is it really possible to have those different types of the rust? So then by the microscopic inspection, the answer is yes. We could see those different type of the rust over there. Another question that I had was, so yes, the corrosion is a big problem. Then do we really care about that in the designing or the construction stage? So this is what I would like to show you. For this research, I had to buy the rebars from the vendors. So we've picked it up the quite famous vendors or bigger vendors in the US. And then this is can you see that on the left two pictures? That is actually the rebar that we just received. It's already corroded significantly. So we had to return this rebar to the vendors, and they have no idea why we returned those rebar. So we explained that, hey, we are gonna just work on the corrosion of the reinforcement. You have to send us really intact rebar, but it was almost impossible. Another photo that you will see on the right is that reason that they just sent us a rusty steel is because they stored like that one. And then on the bottom photo, just show that. So that is a kind of column cage. So before the casting the concrete, they just build the structure, the rebars cage. And then it's already rusted. Can you see that? So even before construction, so do we really care about the corrosion of the rebar? So that is the kind of question that we just had. So this is kind of ugliness of the corrosion that I have seen while doing a lot of experiments. Actually, we are going to do some structural tests after accelerating the corrosion of the rebar. However, it was not really easy to do this experiment because sometimes you just see the liquid type of the rust is coming out of the concrete specimen. That is just okay. However, while doing that, we need to have a rebar. However, it's just gone. You just snap it off on the top of that, so we really cannot pull it out. There's no piece over there. Sometimes we just leave it and just accelerating the corrosion. The rebar is just popped out. Sometimes rebar is going to be remained. However, if you really take a look at inside of it, that is disconnected. So I was quite surprised because of this kind of thing, because I mean, we cannot really expect what's happening inside of the concrete because of the corrosion. And also, that's why it's really hard to predict. Even I'm not sure that it's possible to monitor how much the corrosion is happening inside of the concrete. So what? So this is quite the summary of the current practice. So to care about the corrosion, what we have been doing. So ACI 318 building code just specify about the concrete material. How? Just setting the limit of the water cement ratio and the minimum strength. So in other words, making concrete stronger to slow down the corrosion process. Another way to do that is putting a little bit more thicker cover depth. That also slow down the penetration of the chloride. As a result, it can slow down the corrosion process as well. On the other hand, they just recommended epoxy coating reinforcements or any kind of the coating of the rebar. However, is it really possible to prevent it? That is a question. Also, those kind of methods, we just thought that is a prescriptive, which means that, okay, if we do this, then we can slow down the corrosion. However, we cannot anyways predict the level of the corrosion. So we have no idea how to do that. So basically, our research question was quite simple enough. If we know, or if we estimate the level, if we can estimate the level of the corrosion, and if we know about the type of the material, is it possible to predict the structural performance? In other words, the degradation of the structural performance. That is kind of question. So for doing that, I mean, generally the corrosion process is going to take about a few years to the decades, more than decades. So I cannot wait such a long time. That's why we had to accelerate the corrosion. That's why the first part is going to be necessary. And then second part, we have to really check up the structural test. Among all different types of the structural behavior, we just picked it up, the pull-out test, because that is key mechanism for the structural integrity. So this is going to be kind of simple principle about the accelerated corrosion test. So it's a simple galvanic cell chamber. So by using this chamber, we had to just accelerate the corrosion somehow. This is going to be kind of result that I would like to share with you. So what we tracked down was the current with respect to time. So the corrosion is going to start, then the current is going to be decreasing. And then some of the micro cracks is going to be formed, then current is going to start increasing. So by just seeing this history, the graph of the current, we were able to see what kind of thing is going to happen. So current is going to keep decreasing. At the time, you probably cannot see any crack there. And then the current is going to start going up. Then even micro or small crack is going to happen. And that crack is going to be propagated and become wider. Eventually, that current is going to go to almost infinity. So that is kind of simple kind of way to track down the thing. Theoretically speaking, if you're going to define degree of the corrosion, they use a mass loss. However, we cannot really measure the mass loss inside of the concrete. So instead, we just try to track down the charge by integrating the current with respect to time. So then we just try to use it as indicator for the degree of the corrosion. So look at the beautiful cooked specimen over here. So on the left, that is an intact specimen. On the right is the most corroded specimen over there. So by just changing the level of the corrosion, accelerate the level of the corrosion, we just made a specimen like this. And then we just pulled out the rebar to measure the bond strength of the structure. So that is actually the way that we just try to use. If you see that this graph over here, S0 means intact specimen, and S5 is the most corroded specimen. So you see that the profile is going to be significantly changing. Interesting thing is that if a little bit of the corrosion is happening over here, like S1, then bond slip response is going to sometimes is even better than intact one. So it's not always happening. However, we often observe that kind of pattern as well. So this is a New England area. Among the all different types of results, I just picked it up, the three interesting factor over here. So this graph is going to show you the corrosion degree responses between the normal concrete versus air entraining concrete. Because here is the New England area, about the 6% air entrained concrete is the most common concrete. So if you see the response over here, those orange line is going to be higher than blue, which means in the air entrained concrete, the corrosion is going to be more accelerated. So corrosion is going to happen faster. That makes sense because it has more pores inside of the concrete. As a result, this graph shows that ultimate bond strength of the concrete. So normal concrete, if there is no charge, so x-axis is a charge, which means that 0 means no corrosion, and the number is going to be increasing. That means that highly corroded state. So degree of the corrosion is going to be high on the right-hand side. 0 means that no corrosion over here. Y-axis is the peak bond strength of it. So which means that the normal strength concrete, as long as there is no corrosion over here, it's the highest bond strength is going to be shown. However, corrosion is going to be progressed, then that strength is going to be going down. That is just a reasonable thing. However, air entrained concrete is going to be over here. A little bit of the corrosion is sometimes helpful. However, corrosion is going to progress further, then the strength of it is going to be going down. Another thing is going to be about the slag use. Nowadays, a low carbon concrete, the importance of the low carbon concrete is going to be higher. So then a lot of the industry try to use the slag in the concrete. However, here's a little bit of the problem. Electrical conductivity of the slag concrete is going to be higher than normal one. As a result, the risk for the corrosion becomes higher, which means corrosion is going to happen inside of a slag concrete, then it's going to be faster. So that would be a problem. However, slag itself is going to give some filler effect. Bond strength is going to be a little bit better than normal concrete. That is a little bit of a controversial issue. So we just try to interpret this one a little bit further. But anyways, corrosion is going to be progressed anyways, then the amount of the slag is going to be just meaningless. So next. So then on the top of the slag concrete, we try to use a basalt fiber, the top of that. So how it's going to be used. So can you just see that? The blue response is going to be normal concrete as long as you're going to use the basalt fiber. The curve is going to be a little bit lower than that, which means that it's going to be more stronger for the corrosion. So I believe that the fiber is going to somehow minimize micro cracks as well. So then that's going to just slow down the corrosion process as well. As a result, the bond strength is going to be higher when you use more of the fibers in there. So what we found, the three effects: air entraining agent. If you just use the air training concrete, then it's going to accelerate the corrosion. And then if you use slag in the concrete to reduce the carbon footprint, but it's going to be good. However, you have to be careful because the corrosion is going to be accelerated in the slag concrete. If you're going to use it more than 10%, I would say that more than 20% of the slag use is going to be helpful to get the filler effect. And then non-metallic fiber, in other words, the basalt fiber, really helped to improve the bond strength of it. Then how much is going to be good? Then 1% of the use is going to be pretty optimum range of it. So I'd like to finally highlight some of the things that I also have to appreciate to undergrad students that they work together. So I would like to show that their design kind of progress. So 5 years ago, they just start with like this, and they just built from the scratch. And then they just found out some of the heat problem because the corrosion itself is going to exothermic. So if you believe that you are doing this experiment under 20 degrees Celsius, however, corrosion is going to start happening, then temperature is going to go up. So we just try to get rid of the temperature effect. Then we had to just make some cooler system. Then eventually the design is going to be a little bit. So after that, what? Based on the result that we just got, and we just try to get some of the model from there. So just not just a simple regression model, we just try to use a kinetics model. Why? Because the corrosion itself is a chemical reaction. And we are dealing with the mechanical property degradation. So to combine that one, then we try to use the kinetic model for that one. Thank you very much for your attention.